So today's topic is about Duplex transform, which is a little like we will see later. Which we will see later is almost like the condition of probability, just on some condition. So now let's give some. I want to introduce the general theory first, and then just talk about some specific examples. Now we always assume that our state space is countable or finite. This doesn't matter. Just then assume H is non-negative function on omega such that just the zero set of H is finite. It's finite. And PHX is equal to HX for every X not in A. Okay, we call this condition that H is harmonic at the point X. It's harmonic at the point X. Okay. So I could give some specific examples. The first one is omega equal to Z, and Hx is equal to the absolute value of X. Just and here our Markov chain is just the simple symmetric random walk on Z. And the second is a little complicated. Z squared and Hx is equal to the maybe here I should use A or H, whatever. Equal to and here our A is equal to both of A are the original point. And okay.
Can you remind us what is PK? Just
okay. PK here, just for example, PKXY just is equal to PX X. The probability from starting from X of XK equal to Y. Here I use this notation. So. Okay. And here I want to add just admit one more property of A. Just A of X actually is equal to 2 over pi log of the absolute value of X minus a constant called gamma and plus O X minus squared to the power of minus squared. Okay, I will use this later maybe. Okay, now I want there is a proposition is that for every x not in A, h of x and tau A is martingale. With respect to the probability px. Do you want me to prove this, or just accept this? Okay. Okay, now just accept this. Now I want to give H more assumptions. Like I want to give H more assumptions. Like I will assume that first hx just equal to infinity, which means that for this equivalent to say for every A positive, the set H less equal to A is finite. It's finite. And the second thing is that there exists C positive such that the difference between hx and the hy is less equal to C. Just for, okay. For every x and y. For every x and y in omega. Should I? It's fine. Okay. Now let's, from proposition 3, we could get corollary. Just saying that the expectation h of in tau A is actually, since this guy is martingale, so the expectation should be equal to the expectation of h of x0. x0 is equal to x since this Markov chain starts from x, so it's equal to x. And then by the convergence theorem of martingales, then we can know this guy is actually. Oh, sorry, we couldn't do this. Sorry. Oh, here I think I shouldn't use A. Let me use R. Here is lambda R defined by. And this guy now is this convergence to Ex H x tau A equal to this guy. Okay, here this notation means just this notation maybe called Mongolia. I'm not sure. Just means the minimal between m and n, minimal value.
So we usually call it wedge.
Wedge, okay. So by the definition of expectation, we know this guy equal to two integrals. The first one is the tau A less than tau H R, the complement of tau HR and H X tau A plus now let's see. Okay, now we know X tau A must in A by the definition of tau, right? So, and A is the zero set of H, so H of X tau A equal to 0. So now we can ignore this guy. And how about this guy? This guy actually, we know from the definition of tau, the complement of lambda r, we know tau, here is x. This guy should large than r, but we have this assumption. We know h of tau, the complement of r minus 1 is less equal to r. So this guy should less equal to r plus c. And now from this we can know this guy is just about, so actually this guy could be, just this function could be, say, a function, just, well, how to see this? Just, it's around r time 1 plus o r inverse. Just its increasing speed is about like this with respect to r. So here now we know this guy is equal to px tau r c less than tau a, less than tau a. So now we get that px tau, the probability of starting from x of this chain goes out of lambda r before return to A is equal to hx over r times 1 plus this guy. It's about this guy. This is what we have got. Okay. Okay. So now let me give another definition, just the definition of Doob transform. Doob transform is another Markov chain, but please note here is not the reversible probability. That means this, just but they have the same. H of y over h of x, hx now equal to 0, and here is 0. Okay. Actually, we know that then we could check that for every x not in A, this is actually a transition matrix, but how about for the point x in A? So actually, we could just if x in A, we could do like if we want to everything just perfect, or just like if the original chain is irreducible, but here if we take the value 0 here, then it will not be irreducible anymore. So we could just take the original transition matrix. But this doesn't matter because we will not consider the probability x in A. Okay. So actually, we could check that for every x not in A, this guy is actually just transition matrix. This guy equal to by definition of harmonic function. Right? Okay. So now let's do something interesting. Let's do something interesting. Like let me think. It's like okay. Let me use
Just a quick thing. You could observe that according to P hat, you never go to A, no?
yeah. It's not in A.
No, what I'm saying is that
Uh-huh.
P hat now is a transition probability, and this transition probability is such that you never go to set A, no?
Yeah. Yeah. So now we will assume we will use gamma to represent a path just like x0 to x1 to x2 to xn. And we want to, for example, here is our lambda r. Lambda r is here. And since A is finite, so we could just assume that R is large enough to make sure A is contained in lambda R. And the xn, x0, xn, x1, x2, x1, x3, x4, x5, x6, x minus, just like this. Okay, so we will assume that the intersection between gamma and A is empty, and x0 is in lambda R, deleting A, and xn is not in lambda R. Now, how about the probability of these paths? Which means the probability of these paths, by definition, is just this guy. Yeah. Just the path, just the chain for the probability of this Markov chain following this path is just equal to this one.
This is P, not P hat.
Yeah, this is P instead of P hat. But we will also just compute P hat. P hat is equal to P hat x0, x1, P xn minus 1 xn, which equal to px0 x1 x1 h of x1 over h of x0 p x1 x2 h of x2 over h of x1. And minus 1. So here, we could ignore these guys. And then this equal to, actually, equal to p gamma and h of xn over h of x0 equal to this one. Okay, now let me see. This equal to this one, and just using the same argument, we can know the value of h of xn. H of xn is actually in the interval, the closer interval from r to r plus c, right? Just use the same argument what we have done. And h of x0, now, since x0 is not in A, let me use this estimation, the estimation here. x0 equal to the probability of px0 tau, the complement of lambda r less than tau a time r 1 plus or r minus. Then we can know the ph gamma equal to p gamma time here is px0 tau a. But please notice these two blocks here is not the same function, okay? And one of them is h of xn, and the another guy is h of x tau, the complement of lambda r. They are not the same. But what we could get is that this guy, just this term must be equal to 1 plus O, capital O of R inverse, okay? So this guy should be like so now, if we use the, I want to do something not so rigorous, which is to use the definition of like conditional probability. Maybe we could just try to write this but not so rigorous. See this guy as the probability, conditional probability of gamma under the condition, just the path reach the complement of lambda r between A. It's a little like this, okay? And then if we let r tend to infinity, then we can know this guy must be 1, right? Since this term will be equal to 0, and this guy must be 1. And then this guy will be like tau, this guy will tend to infinity. So this conditional probability we could say just like S gamma and tau A equal to infinity, which means that the path will never arrive at the set A. So we could see just the chain under the H transform as the conditional probability, which the condition is that we will never arrive at like A, just like this. So maybe we could give an example. Now let me give an example.
You can go up to 9 if you need to.
Okay. So now it's definition 5 and example 6. The first one is still omega to z, and hx equal to x, the absolute value of x. So now, actually we could just compute this more. So the lambda r actually is just equal to x in z. The absolute value of x less equal to r. So hxn, the absolute value of h of xn must be equal to r plus 1 since what? This is r, and every time we will only jump one length, so this must be r plus 1. But here, I should do this on the real line, but yeah, identifies. So this be, and so h of x tau, this guy also should be r plus 1. So as we have seen, must be equal to px0 less than tau a. Tau a is just a tau 0. And so what is tau? The complement of lambda r. This guy should be equal to tau should be this one, right? Should be this one. Okay. So actually, I think we have done the probability of this guy before, right? Just in our Markov chain class. Just if we want to how to prove like r plus 1 less than tau 0. How to prove this? We have done before, right? It's equal to r plus x0 over r plus 1. Like this. Okay. So this is the first thing, and we have known this before. Let me check. Okay. H0 h of x. And here we could also see the similar result here, just from this guy, equal to p gamma r plus 1 over x0. All right, we get the same result. Just from here and this guy. This coincides with the previous computation, just in the previous class. Since here we know that p x0 tau, this probability should, for example, r plus 1 is just equal to x0 over r plus 1. So actually, this coincides with our previous results. And the second result is omega equal to v squared ax. So I will write just like this guy. As we have done before. As we have done before. Actually, we could get better estimations from this function. The first thing we should observe is that observe is that the difference between ax and ay is less equal to a constant time, or this just means okay. If we use this estimation, actually we could get better results. Let's do this. Just like here. Here we should change a little, just like let lambda r be x in this way. Let's use this assumption. Since when x is very, very large, then the absolute value of x is very, very large, then this function is just a little, it's almost this function, just log x. So we could just, which is an increasing function, so we could just let this set be just like a disk, you know, since this function is just a radial function. It's just a radial function, so we could just see the original set like a disk. So just use this. Just use this notation. It's more convenient. Okay, so p x0. Let me think. P gamma is equal to just equal to p x0 x1 p x and minus 1 xn. And since this squared is just a simple symmetric random walk on this squared, so this guy, every probability must be 1 over 4. Right? So this guy is equal to 1 over 4 to the power of the length of the gamma. Okay, so similarly we could get this guy equal to time ax in ax now we need to estimate AXN and AX0. AXN, first by definition, let me think, is like, let me check if this is right. A of xn is equal to axn over ax0 is like oh, okay. And this difference is about this guy. So now we let me check if this is right. Equal to this one here. Log square.
Because with that definition,
Mm-hmm.
the dominant term is log r. Okay, with the definition that you're using there, it's 1 over r squared.
Yeah. So r to the power minus 2, we could just ignore, just use minus 1 to replace.
Yes.
Yeah. This guy is equal to this one. So this is just equal to AX0. Okay. Now we need to AX0 by our definition is equal to A of X tau less than tau n. A is equal to this guy. Oh, here A is just a 0. A is just a 0. So this guy, as we have said, this term is about still equal to AR plus so is equal to AR plus O X0 Px0 tau less than tau 0, which means that equal to 0 less than tau A time AR plus OR O1, O2. Let me use this to differ these different terms. So we need to estimate this one. This one actually, I think, let me do this. Equal to 1 plus O1, O2, O1 minus O2 AR plus O2. And this guy, when R is very large, is equal to like 1 plus log R plus O. So this term is about so what we have got is that equal to P gamma Px0 less than tau A tau 0, yeah, tau 0. One plus O R log R. Yeah, and this term actually is stronger than the previous estimation we have got before, right? Since we have got before is like this term, and then now we could get faster speed. Just in this example. Yeah, that's all.
Okay.
Thanks.
Thank you very much.
Sadly, my handwriting isn't half as good as Jifan's, and I'm sure my Chinese handwriting is even worse. But hopefully will be understandable nevertheless. Okay. I think I can erase the rest. That's fine as well. Okay, so should I start? Yeah, so I wanted to talk to you about GMP a bit. So I don't think we have defined GMP so far, so I'm going to start defining it. Then we're going to see the main problem we're going to tackle, although it's far from the only problem, from the only interesting problem in GMP. And then we're going to see a sort of like, not necessarily modern approach. We're going to see something that's, that the professor talked about, or rather touched on very briefly, which is Poissonization. And we're going to see how it helps us to solve the problem in a much faster way and in a much cleaner way than the traditional way, maybe. So okay, so maybe an introduction. So what is GMP? GMP is probably one of the first, if not the first, random graph model you could consider, right? So is that size right? Is it readable? Good. So it has two parameters, n, which is some integer, non-zero integer, a positive integer, and some p, which is some value in 0 and 1. A priori, there's no problem with letting p being 0 or 1, but I'm going to exclude it because it's really not interesting in that case. And the p, I want you to think about it as a function of n. So it's not some fixed constants, it's a function of n. Although, of course, a fixed constant also makes sense, right? So what is this model? So it's a random graph on n vertices, right? So random, sometimes called binomial, also the Erdős-Rényi model, because it was introduced in the 60s by Erdős and Rényi. Random graph on n vertices. Where each edge is present independently IID with probability p. So let's do a little example. So usually I'm going to think about n going to infinity, but just so we get the hang of it, let's do g6.5. So what would this be? This would be a graph on 6 vertices, and I look at each of the pos of I don't know how many, 15, each of the 15 possible edges, and for each one of them I flip a coin, an unbiased coin in this case, to see whether the edge is present or no. So I look at this edge and I say, oh, I flip a coin, I'm going to flip it in my head. It's going to say it's tails. Then I go to the next one. What about this one? Oh, that is heads. This edge is not present. And I do that for every edge. And I'm not going to draw them all, but I'm sure you get the idea. And that you do for all possible 15 edges, right? So maybe in the end, you end up with something like this. OK? Is the model clear? Yeah. So there's a lot of questions we can ask about it. All of them interesting for very different ranges of p, very different types of questions. It's probably, at least in combinatorics, one of the most revolutionizing objects when it was introduced, even if it wasn't so clear at the moment. But now we're gonna worry about maybe the first problem actually considered in GMP, which is the giant component, right? So what is this giant component? So the phenomenon we're going to be interested in is, when does this graph, remember we're always thinking about the number of vertices going to infinity, and p a function of n, usually going to 0. In our case, it's going to go to 0. And the question is, how big or small has to be p so that we find, with some decent probability, meaning going to 1 when n goes to infinity, a component of linear size, right? And we would hopefully, like, our dream would be to say, oh, if p is like bigger than this, then you find a component of linear size. Maybe it's unique. And if it's below that threshold, then you don't find any components of linear size, any connected components of linear size, right? That would be the dream, and that's actually exactly what happens in this case. You can also start asking other types of questions once you solve this problem, which we're not going to do right now. But just to give you a taste of the stuff you can do, you can ask, okay, what is the structure of the components? Aside from the big component, when I have a linear size, what can I say about the other components? Are there root size? Are there logarithmic size? Are there any isolated vertices? Those kinds of questions are all stuff you can ask, and there's a very, very rich theory about it, which I of course I'm not going to have time to talk about. But just know that this is something very, very well studied. It's a very, very famous problem that a lot of people have worked on since the 60s. Although there was a bit of a hiatus from the 60s until the 80s, from when this model was introduced up to when people started actually caring about it. So again, what is this problem? Or maybe I'm just going to state the theorem. If p P is of the form C over N, which turns out for not so hard to see reasons, though I'm not going to do it right now. This turns out to be the right normalization parameter, a function of the form some constant over N. Then the probability of GMP having, I'm just going to say component, but I always mean connected component, right? Component of linear size goes to 0 if P is if C is smaller than 1, and to 1 if C is bigger than 1. This is the threshold phenomenon we're going to see. So you have this P, which is some function of N, right? C over N. If this constant is smaller than 1, then you have no components of linear size with high probability. And if with high probability always means that the probability goes to 1 when N goes to infinity. And if your constant is bigger than 1, then you do have a big component. Okay? I'm going to give you an intuition for why this should be true. And then we're going to prove actually a sharper result than this. We're going to see that actually in this second case, there's only one component of linear size. And we're going to calculate what is the implicit constant. When I say linear size, what is the constant, right? There's also a question what happens in C exactly equals 1. That is actually way harder. So I'm gonna maybe talk about it at the end. I'm definitely not gonna prove it, but I'm gonna talk a bit about the structure of the component, so you get an idea of what's happening, right? So actually, we're gonna prove something a bit sharper than this. But let me give you an intuition of why this should be true, right? So imagine you wanted to prove something like this. So what is the first, or not maybe not the first, but what is a reasonable thing to try? Well, we're gonna do what's called an exploration process, right? So I'm going to start with some vertex arbitrary of GMP. All of them at the start, they're all the same. I'm going to reveal its neighborhood. What do I mean by that? I'm gonna sample all the edges connected to this vertex, and I'm going to see where the coin landed, whether it's an edge or it's not an edge. What is, maybe as a first question to see if we're all on the same page, what is the distribution of the number of neighbors of a particular vertex? Binomial, right? So it's binomial. The number of vertices of the number of neighbors of B is binomial n minus 1p. In our case, P is like C over N, right? And this is sort of for large n. This is sort of like a Poisson of parameter C, right? So I look at the vertices, and it has a Poisson neighborhood, right? Then I could do it again. I have this constant number of neighborhoods that is sort of constant, right? A Poisson is sort of like well concentrated, so reasonably enough concentrated. So I have this Poisson C, which is like some constant number of neighbors, and then I'm going to do the same thing for every neighbor. Now I look at the neighborhood of this guy. For the same reason, this is also like a Poisson C, right? Why? Because, okay, I'm not looking at all the neighbors. I'm not considering either V or all these possible guys, but actually on the first step, this is like a Poisson C still, because I took away few vertices. I took away, like on average, like C plus 1 vertices, right? So I continue this process. I do the same thing for this. And actually, the proof for the giant component, the classical proof, sort of goes like this. I'm cheating a bit, right? Because it's not actually a Poisson, and actually I'm losing a bit. And actually, this breaks down after some point, because the approximation is not so good after, say, root n steps, right? But the classical proof goes sort of like this. And now what would happen? Well, if C is smaller than 1, then on average, every guy gets less than one neighbor, right? So you expect this process to die out. So imagine for a second we're in this idealized process where I don't have to care about the previous ones. Just every guy has Poisson C neighbors. They never repeat, right? There's also, I maybe forgot to mention it, but there's also a probability that this guy and this guy have some other common neighbor, right? Let's think about this idealized process, which is called a Galton-Watson tree. That doesn't really matter the name, but it's like this idealized process where you, every time you look Poisson C neighbors, and you could ask, well, what is the probability that this process dies down rather quickly? And it turns out that if C is less than 1, then this process dies out. I'm not going to prove it because it's not going to be relevant to us, but it makes sense. If I have a population where every person has on average less than 1 kid, then the population is going to die out rather quickly, right? On the other hand, if C is strictly greater than 1, let's say 1.3 or 1.2, whatever, every person is having more than 1 child on average. So you expect that the probability of this process going on forever should be positive. Not going to 1, right? Because in the first step you maybe lose. But if you manage to get like a head start, then you should be able to with a very decent probability go on forever, right? This is just an intuition. I'm not going to prove any of this because it's not going to be relevant to ours. I'm just trying to give you the intuition of why this is a very reasonable theorem, right? So that's the intuition for why we should expect something like this to happen. The problem is that, and you can try to do this at home, actually getting this intuition into something real is quite hard. It's really quite hard because at some point you really start to get the dependencies. At some point you really start to get these cycles, these vertices that share neighbors, and that's what messes you up actually, cycles. That's like the main problem. So this can be turned into a proof with a lot of elbow grease, doing a clever coupling and stochastic domination and all those clever words. But I'm not going to do that. So let's do one step of this process and see what happens, and then we're going to introduce the main tool we're going to use. So I think one of the main problems, this Poisson approximation is not the problem in the first step. In the first step, this is actually a very good approximation. It's later down the line, but let's see what happens in the first step. So in the first step, I have this neighbor, and it has some neighborhood, which has distribution basically Poisson C. Has this neighborhood. And conditioned on the size of the neighborhood, this graph inside is a copy of GMP for a different n. Right? This is a copy of G. This has, when I say a copy, I mean this has distribution n minus the neighborhood of V. Well, n minus 1, I guess, because I'm also not considering V, comma P. The problem is that this is a random variable, right? If I conditioned on the size of the neighborhood being decently big, then this guy would be a copy of G n minus 1 minus some constant times P, right? That is something good because we could have this. Well, if we condition on the size of the neighborhood, this guy looks a lot like the original object. So we could hope to do something not inductive in the literal sense, but something like at smaller scales, right? The same problem at smaller scales. The problem is that this is a random variable. It's a Poisson random variable. So when I look at this doesn't have distribution GMP. This has distribution like G n minus a Poisson P, right? That is the main problem. How do we fix this? We're just going to create a new model that we're at the end going to couple with GMP that is just going to have a Poisson number of vertices. And this is actually going to solve our problem very, very neatly, very cleanly. So maybe I'm going to define a new model, which I'm going to call, so given alpha positive, this is going to be, I want you to think of alpha as being n, and p in 0, 1. We define this G Poisson alpha p as the following. So I want you to think of the following way. I first sample a Poisson random variable, which is going to be some, let's say, big N. So N has some distribution Poisson alpha. So I'm going to sample this N with a Poisson random variable, and then I'm going to look at GMP on N many vertices, independent of N. So sorry, sampled N, I do everything independently, given N. Okay, so does the model make sense? So I first sample the number of vertices, and then I run GMP on that number of vertices. Okay? And now the funny part is that this guy, this new guy, which seems sort of more complicated because I'm not fixing the number of vertices, actually satisfies a very nice Markov property in the sense that we're going to get the same model inside in the neighborhood. So maybe I'm going to but first I have to do a clever step, actually. So that is intuition, but there's a clever step that fixes things. So this I'm going to call the core. I'm going to call the core, yeah, but I'm also going to have a stack of infinitely many vertices together with a stack of infinite. I'm going to do a drawing so that this isn't too abstract. Infinitely many vertices. Countably infinite, that doesn't really matter. Let's say countably many. Many vertices. Each of them connected to the core, to each vertex of the core, independently with probability P. So let's do a drawing. So let's say I sample my n. I have this Poisson. I have these Poisson many vertices in which I run this GMP. So this is like this G. I'm going to call it like this, NP. But remember, this n is a random variable. And I also have this outside of the core. I have this. This is maybe the cleverest step. This stack of infinitely many vertices. And for each guy here, I look at each of the vertices and I add this edge with probability P, with the same P as here, right? So I have this guy, and do that for every vertex here. So maybe this edge is present as well, maybe this one isn't, etc. And I do that for every vertex, right? And just to be very explicit, there's no edges in between the vertices of the stack. This stack is just want to help so that the calculations are prettier. So that the calculations are prettier, right? So okay, so this satisfies a very nice Markov property, which I'm gonna write here. So just to don't write anything that's not true. So lemma. This Markov property is going to be exactly what I was telling you, is that after I take out a vertex and its neighborhood, the model is basically the same. It's still the same model with the slightly different parameters. So so the way the exploration process is going to work is I'm going to take the vertex that's at the top of the stack. I'm going to look at its neighbors. I'm going to reveal the edges in between here, right? I'm going to look at its neighborhood, and I'm going to take it out of the core, and I'm going to put it at the top of the stack. And then at the next step, I'm going to look at the vertex that's at the top of the stack. I'm going to reveal its neighborhood. I'm going to take it out, put it at the top of the stack. I'm going to continue doing that. Okay, so let k, this is a random variable. It's the number of neighbors in the core, which are the only neighbors actually, in the core of the vertex at the top of the stack. Okay. Then K has Poisson distribution. This is not very surprising. Alpha times P. This shouldn't be very surprising, right? It's the same thing we were talking about before, so, except that here it's actually a Poisson, right? Because it's not binomial anymore. And the graph conditioned on k the core without the neighbors of the neighbors has distribution, has, let's say, law G Poisson alpha 1 minus p p, right? So what is this saying? So I have my stack here, which I'm queuing one by one, and I have my core here. And again, I look at this guy, I reveal its neighborhood. It's these three guys. So in this case, in this drawing, k equals 3, right? I take this vertex, these three vertices out of the world. I put it on the top of the stack. The first thing I'm saying is that the number of vertices follows a Poisson law. And the second thing I'm saying is, if you know how many vertices I took out, then this remaining graph still has this Poisson distribution, which is something that we didn't have before in GMP. This is what we lost in GMP, right? This is no longer a copy of GMP. There is this Poisson or binomial, but like almost Poisson random variable floating about, which we didn't have before. Now we only have stuff that we had before. Okay, with slightly different parameters. That is clear. That you couldn't hope for anything different. Slightly different parameters, but it has the same law basically. It's still a Poissonized GMP. That's the name of this weird object. Okay, and the proof is actually quite silly. It's just a computation, but that doesn't make it any less important. It's any less useful. So let n prime be n minus k. So this is the number of vertices in the core after I took out the neighbors, right? And we're gonna calculate this. So the probability of k equals k and n prime equals n. This is, of course, if you're used to these Poisson calculations, this is a very standard thing to consider. We're gonna see that these two are independent, which is one of the classical properties of Poisson random variables, and that k has a Poisson. So how are we gonna calculate this? So I think it's just this. So this is the same as the probability of k equals k and big N equals n plus k, right? And now we're going to condition on big N. So this is the probability of k equals k, given that big N equals n plus k, times the probability of big N equals big N equals n plus k, right? Now, what is this, guys? This is, so out of the n plus k vertices, I have to choose exactly k. Condition on the n, this is just a binomial random variable, right? Because if I condition the number of vertices, each edge is with probability p, so each guy is a neighbor with probability p, so the neighborhood is a binomial random variable. So this is just the probability of a binomial on n plus k guys equals k. This is p to the k, 1 minus p to the n plus k minus k, right? And this is just a Poisson random variable, right? This is, well, e to the minus alpha, alpha to the n plus k over n plus k factorial, right? We're gonna do. I'm maybe gonna write the next line, and then we'll see why they're the same. So I'm saying that this should be the same as, well, alpha p. So it should be e to the negative alpha p to the k over k factorial, e to the minus alpha 1 minus p, alpha 1 minus p to the n over n factorial. I'm claiming that the second to last line and the last line are the same. That should be obvious. If you expand this guy, the n plus k factorial cancels with this n plus k factorial. I get a k times n plus k minus k, which is n factorial. This is k factorial and factorial. This guy, if you put them together, they're of course the same as e to the negative alpha. I have p to the k, 1 minus p to the n, alpha to the k, alpha to the n, and that's all, right? So this is just a simple calculation, and this is of course the same as the probability that k. Sorry, maybe I should write it like this. This is the probability that a Poisson alpha p equals k times the probability that a Poisson 1 minus alpha p equals n. Right? So this implies by definition, actually, of independence, that this guy has distribution Poisson alpha p, that this guy has distribution Poisson 1 minus alpha p, and actually they're also independent. Right? Make sense? So this is a very silly calculation. It's a very common calculation as well to do with these Poisson random variables. But it's nevertheless a very important property. This Markov property is what's going to turn this from a very hard problem, this GMP guy, from a very hard problem where you have to couple it clearly with a Galton-Watson tree, and then you have to see that it doesn't get messy too quickly, and you have to do a stochastic domination, and you have to prove all this stuff into a very like tangible problem that you can, at least the heuristics you could do in an afternoon. So it's very pretty, I think. Okay, so this is going to be the main thing, this lemma. So it's so important that maybe I'm not going to even erase it. So I'm just going to keep this board as is. Okay, so again, we're running our exploration process, and the next clever idea is a combinatorial idea, which is we're going to define the following. So again. So maybe I'm gonna repeat what's happening here. So I'm doing this exploration process, right? So I'm looking at the neighborhood of one of the vertices of the stack. I'm putting all the vertices of the stack on top, and then I'm looking at the vertex on top, and I'm continuing this process. So what happens if I keep running on this thing? I will put this guy on top, right? And he's gonna have some neighborhood in the rest, right? Then I'm gonna put this guy on top, and this is gonna have some neighborhood in the rest. And at some point, these neighbors, I'm not gonna have any more neighbors, right? So then I'm gonna go, so this is gonna be on top, but it's not gonna have any neighbors. So I go to the next one, and maybe this guy also doesn't have any neighbors, and maybe this one, and I'm gonna continue. And at some point, I'm gonna sample all the connected component associated to this vertex, right? So, and I want to see how long it takes me to run the connected component of that vertex, right? So we're gonna define this process. So define sk by s0 equals 0. This is just the starting step, I guess. And sk is gonna be the previous one. This is a random walk, I guess, plus the number of neighbors discovered in step k. So it's how many neighbors I've seen so far, basically, minus 1. This minus 1 actually, although seems unassuming, it's playing a very important role. It's telling our algorithm, if you want to think about it, when to stop. When have you finished a connected component? Imagine I didn't have this minus 1, and we'll see what's the problem, and then we'll see how the minus 1 fixes it. So imagine I give you the sk. I don't tell you the process I run. I mean, I tell you how the process works probabilistically, but you're not able to see the graph. So I'm seeing the graph. You know it has a Poisson. It's a Poisson graph of parameters alpha p, but you don't know exactly what the sampling is. So I just give you the output of the sk without the minus 1 for a second. So you say, OK, I discovered so many neighbors this step. I discovered so many neighbors this step. And then you see, oh, I discovered 0 neighbors. OK, that meant that I get to a leaf, to a guy that doesn't have any neighbors outside. But that doesn't mean that I finished a connected component, right? And then I go 0, 0, 0, 0. So the SK is unchanged for a bunch of steps. Okay, I got a bunch of leaves, and then I get 3 vertices. So there's 2 things that a priori could be happening. The first thing that could be happening is that I finished a connected component, and now I'm looking at a new vertex from the stack. The second thing that could be happening is that I had all these leaves, and then I had these 3 neighbors of one of the leaves, and I'm still in the same connected component. Just from the SK, you cannot tell anything. This -1, although unassuming, will actually make the difference. So this -1 is going to let us detect when we finish a connected component just from the SK. So then we're gonna have to worry in the SK. So I'm gonna do a little drawing. This is maybe the most important part, I think. And I'm gonna do the same drawing I had over there, right? So I don't want to do it too bad, so let's do something like this, maybe. So not too many vertices, and then something like this, and then maybe this guy doesn't have any neighbors, and then something like this. Okay? So let's see what the SK is doing. So it starts at 0, right? Then I'm sampling this vertex, right? So in the first step, I won a vertex, right? So I discovered 1 guy, but I have to subtract 1. So at the next step, it's still at 0, right? Okay, next step. Now I have to look at this guy. So I won a vertex. Sorry, I have to look at this guy, right? So I want 2 vertices, right? So I want 2 vertices, but I have to subtract 1, so it goes up 1 unit, right? Make sense? I want 2 vertices, and I have to subtract 1. That's what I'm doing. Then I go to the next step, and I say, oh, I want 0 vertices, so I have to subtract 1, right? Because I want 0 vertices, but I'm always subtracting 1. So I finished with this guy, right? Then I go, okay, next guy. Okay, so this guy, I want 1 neighbor, but I have to subtract 1. So I'm at 0 again. And then I go to this guy, I say, oh, I want 0 neighbors, and I have to subtract 1. So I go to -1. Then I'll go to the next vertex. The next vertex, okay, I want 1 neighbor, so maybe this vertex is going to be white, this is going to be blue, this is going to be yellow, and this is going to be red. Just so the diagram is easier to look at. And I really want to spend a bit of time in this drawing so we see what's happening. So okay, now the next guy. I want 1 neighbor, so I add 0, right? Because it's the number of neighbors -1. Okay, so 0. Then I look at this guy. Oh, I gain 1 neighbor, so I have to subtract 1. Sorry, I have to 1 plus -1, which is 0. And then I look at the last guy and say, oh, I want no neighbors, so I go down 1. Then I go to the yellow guy, say, okay, I want 0 neighbors, so I have to subtract 1. And then lastly, I go to the red guy, and I say, oh, I got 1 neighbor, so I stay still. And then, well, actually, maybe I'm going to do it like this, just so it's a bit more interesting. Then I want 2 neighbors, so I have to go up by 1. Then this guy wants 0 neighbors, so I go down by 1. And this guy got 0 neighbors, so I go down by 1. And it's good that I didn't do any more vertices because my drawing is leaving the board. So what's happening is that at this point, the minimum records is whenever I finish discovering a connected component. So what's happening is, since winning 1 neighbor, I'm not counting as anything, when I get 1 below the previous record, it means that I just finished a connected component. Think about the first connected component, and that is just the same thing from the next vertex, right? So actually, the times where I break the minimum record, so maybe the nice observation is the following. This is just a very silly combinatorial argument. These -1s should not change anything, right? But this -1 really gives you a really good metric to keep track at any point whether whether you finish a connected component. Otherwise, you would have to see the whole sequence of sk and sort of like reconstruct it step by step. Now you just keep track of the minimum. When was the last record? So now the observation, the minimal record times maybe it should be the record minimal times. Well, times happen when I finish discovering a connected component. When we finished exploring a component. So if you wanted to find out the size of a component from this graph, all that you would have to do is, okay, I start from the first guy and I say, oh, when did it break the record? So when did it go under this guy? And I say, okay, it's this guy. So the size of the component should be 1, 2, 3, 4, 5, 6. And we see, minus 1 because there's a counting thing. But 1, 2, 3, 4. Sorry, 1, 2, 3, 4, 5. So 5, right? Then I say because and then I see because the component doesn't start at the vertex 0, right? It starts here. And then I see, okay, what about the next component? It's 1, 2, 3, 4. So it has size 3. We look here, 1, 2, 3. Okay, great. What about here? It has size, okay, 1, 2, so it has 1 vertex. 1, 2, 3, 4, 5, so it has 4 vertices, right? So a very good metric for the size of a connected component is just the difference of times of the minimal record times, okay? So how long did I go without breaking a record? Okay, this is one of the really key observations. That one is a very nice idea, very good idea. This is like the key observation, right? It's like the clever bit, right? So, okay, does this make sense to everyone? Okay, good. And now what I want to, I shouldn't have erased. Well, that's fine. And now the observation is out. Of course, the SK, you can keep doing this. And the number of neighbors I discovered, you can do an induction, right? The number of neighbors I discovered in step K is a Poisson random variable, right? So this SK is a sum of Poisson, the Poisson alpha plus, alpha p, I guess, plus Poisson alpha p1 minus p plus Poisson alpha p1 minus p k minus 1 minus k. This minus k is because at each step I'm subtracting 1, right? Yeah. So now a probabilist would call this up. I'm gonna tell you what they would call it. They would call it a standard unit rate Poisson counting process on R+. I do combinatorics, so I'm just gonna call this a Poisson random variable. So this is since the sum of independent Poisson random variables it's a sum of it's a Poisson of the sum. This is the same, and this is a geometric sum, so I'm just gonna do it all in one step. So this is alpha and 1 minus p to the k. It's a Poisson random variable minus k. Okay. And again, the sum of independent Poisson random variables is the Poisson of the sum. If you didn't know that, you should have, but now you know it. And the proof is very simple. It's just you open the counts for 2 variables and then you do induction. Okay, and the only observation we're going to use about Poisson random variables, aside from this, is that the limit when t goes to infinity of Poisson t over t equals 1 almost surely. And this is an easy consequence of the law of large numbers, right? But what I said, a Poisson t, you can think of it as the sum of t Poisson 1. Okay, if the t is not an integer, you have a fractional part that actually goes to 0, and everything works out. So this is just a consequence of the law of large numbers. Okay. Okay. Now we're ready to actually almost like sort of finish. These were all the ideas we needed. So a proposition that maybe for time's sake I'm not going to prove, but actually it's not a hard calculation, is the following. Proof is the following. So proposition S and T, this is the floor function, S and T over n converges in probability as n goes to infinity to 1 minus e to the minus ct minus t. Now I'm lying in two parts here. This is true for every t, but actually what I'm going to need, it's not that it's true for every t. It's that, this is for our values of p, right? So for alpha equals n and p equals c over n. So this is true for every t. That is not a lie. What we actually need is that this is true uniformly, meaning with the uniform norm. And also I'm lying because this is only true in every compact. And I actually want it to be on the whole line. There is a trick for that I'm not going to touch on, but it just has to do with concentration of Poisson. I can actually, with high probability, ignore an infinite tail, so I can just do it on compact sets. So I'm lying in two parts, but I actually want you to think about it as this. And this also is just an easy consequence of the law of large numbers, together with, so meaning that the proposition, I didn't write the calculations, but together with the proposition that 1 minus c over n to the nt converges to e to the minus ct. Yeah, and this is the classic definition of e that you saw in Calc 1 or whatever, right? So you use this together with the law of large numbers in the way that is presented there, and you get this convergence in probability. And again, with these little caveats that I'm not going to worry about. So we have this funny function, 1 minus e to the minus ct minus t, and I'm going to do a graph of this function for 3 values. So actually, maybe like this. This is, let's call this guy f of t, fc of t. So we first have the green graph, which looks like this. Bam. This is fc of t when c is bigger than 1. So it starts off at 0, and then blah, 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 it intersects at some number I'm going to call beta of c, this largest root, right? When c equals 1, the drawing looks a bit like this. So it's like tangent here, and then it goes like this. I'm being a bit exaggerated maybe. But it's just so that we have like the rough shape. So it's f1 of t. And then we have this other drawing where it's not tangent anymore. It just goes like this, right? And this is, you guessed it, fc of t for t smaller than 1. For c smaller than 1, I should say. Okay, so we have these 3 graphs, and now I'm gonna convince you that we finished the proof. And then if I don't know if it's worth it, we can actually do the calculations. They're not hard. They just require a little bit of a trick. but what is happening? So what's happening is that this guy, this SNT, this SNT over n, is converging to this function actually uniformly, so in the uniform norm. So if we want to look at if we look at this SNT, this sort of looks like this function, right? So it looks maybe like this, and then maybe something like this. Maybe it's above for a while, but it's always very close, right? And then here maybe it takes just a tiny little bit going to 0, but it gets to around here about at the same time, right? So what's happening is that with high probability, this function this SNT is like, has about this shape, this SNT over n. So we start at 0, and what do we get? The first minimum. So it never goes below 0 until here, until beta of c. So beta of c is when I arrived at the first time I beat the minimum. And remember, I erased it, but when we beat the minimum is when we stopped exploring a connected component. So what is happening in reality is that I'm following this guy. It never breaks a minimum, or maybe at the very, very start it breaks like a small minimum, but then it never breaks a minimum for a long while, and then a beta c. So we should expect a linear connected component of size asymptotically beta c times n, and we also shouldn't expect any more connected components, right? All other connected components are no other linear size connected components, because now it's just decreasing. You're breaking minimums all the time, right? So this is the intuition. Now what happens with c equals 1? C equals 1, you're always breaking minimums. You never get an increasing guy of size like epsilon n, right? You're always breaking minimums, so you don't have any large connected components. And for c equals 1, what should we expect? So maybe this is an intuition. So for what happens at exactly c equals 1, though I'm not going to prove it. So it also doesn't have a connected component of linear size, but maybe you get connected components of bigger size than in this guy, right? So maybe instead of showing you how to turn this into calculations, which is I promise you it's an easy exercise. It's an easy exercise. It's really not hard. It's really not hard. Now how do we finish? Because we did this in this Poissonized model. How do we go back to our original problem? Well, that is actually quite easy. That follows just from a concentration of Poisson, right? So, and there's a clever coupling that I dare not write explicitly, but it's very simple. So, with high probability, Poisson n, I'm going to write it like this. The numbers you actually need are basically smaller than a half, because a Poisson has deviations of size like root n, but actually you need just a tiny bit smaller so that the coupling works and everything else. So the correct numbers, here they do them, just so I don't lie to you. It's like 5 over 12. Here it is, 7 over 12. 7 over 12. So this happens with high probability. It's just because I want both of them to happen at the same time, and there's some silly calculations of why you need this 7 over 12, and so there should be an easy coupling between. So I'm gonna call this guy n minus, and I'm gonna call this guy n plus. So there's an easy coupling between this guy n minus p, always contained in G n p. Maybe I shouldn't call it n, right? Because n was my random variable. So all of these are small n's.
Maybe the n minus and n plus you could call it p, no? Because they are random variables.
I could have called it, no, n plus is the parameter of the Poisson. So that is n plus and n minus. And so you get this coupling. You can always find, you can get an easy coupling just because of this, that with high probability, this Poisson is contained in this guy, and this guy is contained in this Poisson. And then, of course, they have asymptotically the same size connected components, right? Because these guys, it's not changing the size of the connected components. If they were linear before, this is a sublinear term, right? So this implies that GMP has asymptotically the same size connected components as these guys. So okay, so maybe I'm not going to do the calculations for this. They're really not hard. I'm not skipping over anything clever. But I want to talk to you about actually what happens in the correct regime. So just to finish off and leave you with the full theorem, right? So theorem: the probability of GMP GNC over n having linear connected component linear connected component. And it's always unique. When it has this, it's unique, and it has asymptotically that size that I'm not going to write, just so I don't write too much. Is sorry, I should say the probability. I'm going to write I'm going to write like this: the size of the largest connected component of GNC over n. So this C1 is just to say this is the largest connected component of the input. So the size of the largest connected component is big O of log n if C is smaller than 1. So this is this drawing, the orange one. You maybe in the first log n steps break some minimums, or sorry, maybe it's the first steps you do something unexpected, like you go up and then you go down, but after that you normalize. It's theta of n to the 2 over 3 if C equals 1. So what happens here is, since here is tangent, you have more time to do this weird stuff about time n to the 2 over 3, and then it's asymptotically actually beta C times m plus little n if C is bigger than 1. Where again this beta C is this root of this weird function. So you have these three regimes, right? First, when you're C less than 1, all your components have logarithmic size at most. Then all your components, your largest component is of size like n to the 2 over 3. And then when you get to the regime C greater than 1, you get one unique, which I didn't write it here, but one unique linear size component of size beta, basically beta of C, a proportion beta of C. And this is what this actually they do this, if I'm not mistaken, in the first or in the second paper introducing GMP, Erdős and Renyi, and they call this the double jump phenomenon, right? Because you have two jumps from logarithmic to polynomial, but sublinear, and to linear. Double jump. There's a very funny thing that happens, that this is actually a false double jump. There's not actually a false double jump. So what happens, and this I like very much, although the counting is very complex, that when C equals 1, you actually have a different regime. You have to worry about things of this size, lambda n to the, maybe you remember? 4 over 3, right? Like this, and it happens that the size of the largest component is actually a smooth function in lambda. So it interpolates perfectly from log to polynomial to linear. So that I find crazy. So this double jump that they coined in the 60s, it's not actually a double jump. There's like this very clever, or sorry, not clever, this very like small regime that perfectly interpolates smoothly actually from log n to this polynomial to this guy. So for lambda equals 0, this function is going to be this. For lambdas of size like n to the, well, whatever it has to be, n to the third, I guess. N to the third, you get a this, and well, well, whatever lambda has to be. I'm bad with the numerology.
Also minus infinity and plus infinity.
Yeah. And so you get this nice smooth change. That of course is outside of the scope of what I can do now and of what I can do. Period. I don't remember the proofs. So, but it's a very nice thing that happens. This double jump. So I hope I had to skip over some details, but I hope the main idea was clear. Like this clever idea of doing the Poisson thing, just so that we have this Markov property, this very important Markov property that we're basically looking at the same model with different parameters, which we didn't have in GMP at all. And then this idea that by the law of large numbers, this minus 1, which is a very clever combinatorial idea, this minus 1 over here, right, which is a minus k over here, that tells you, okay, when you break a minimum, that's your connected component, and then you have this nice graph, then you're done. Okay? This is actually a very recent proof. This is from 2022. It's a very, very nice idea. Very old problem, very recent proof, and very nice as well. Okay, thank you.